Okay, so what we're going to do is investigate some different kinds of derivatives, and we're going to come up with a very awesome trick. So if we were to do just any constant, that's kind of the premise that we're getting to. So if I asked you to graph f of x equals 3, so that would just be this function, and I asked you, well, what's the slope at that point? I hope all of you would say that the slope along this entire line is 0. And is that true for all constants? If f of x equals 7, f of x equals 1,000,000, what's the slope at any one of those? The slope is 0. So if you are asked to do some more of these problems, what I'm going to do is just give you the derivative and see if you can tell me what the rule is, because there is a rule. What I'm going to do is just write it as 6x minus 2. As I look at the next one, the derivative is negative 15x squared plus 4x minus 3. As I move on to the next one, the derivative is negative 9x squared plus 24x cubed. If at any point you see the pattern, go ahead and write it down and see if you can get the correct answer. 2x to the negative second power minus 6x to the negative third power. And if your rule, if you think you're right, your rule still works for rational exponents. I'm actually going to say it out loud. You do 6 times 2/3, which will give me 4x to the negative 1/3 power. I was supposed to say third. And then minus 8x to the negative third. And if you think you figured it out, I'm going to go ahead and tell you. If you still want to try and think of it on your own, continue, just pause the video, figure it out. But what you do is you take the exponent and you multiply by the number in front, the coefficient in front, and then you subtract 1 from your exponent. And it still works for all values, like even this, because if you do negative 2 times 1, you get negative 2. And if you want, you could write x to the 0 power, because you subtract 1, but x to the 0 power, that's 1. No need to write that. And it still works if you talk about like x to the 0 power, because 0 times anything is 0. Now, you don't really want to think of that as being subtracting 1 from that exponent, but the rule still works. So you get negative 5 times 3 is negative 15. 3 minus 1 is 2. 2 times 2 is 4, x to the first, and so on and so forth. So if you want, you can pause the video and try and figure out some more of these on your own, or you can just copy it down. I'm going to double check that I did my arithmetic correctly. All right, and then I'm going to continue on and do the next one. And it magically changes colors on me, even though I didn't press anything. Negative 6 times negative 1/2 is positive 3. When you subtract 1 from that exponent, it's a negative 3/2 power. And when you get a lot of practice with this, you'll be able to do this math in your head. As I have had lots of practice with subtracting 1 from negative 1/2, so this is kind of natural for me. So here's where we're going to go with this. What can we infer is the derivative with respect to x. This is just the notation that we use this is actually called Leibniz notation. So the derivative with respect to x of x to the n power, you move the n in front times x to the n minus 1 power. If it helps at all, this phrase is basically like take the derivative of the following function. I guess would be the way of thinking it. So this is your indicator to say, take the derivative of this and it'll equal this thing. And you'll get so used to this that it'll be, second nature once we get into a lot of problems. So we call this power rule for differentiation, and it works for anything that can be written as a polynomial. Now notice that some functions look like they're rationals, but if we were to look at f of x here, because it's dividing by a monomial, you can just divide every piece by that. So now, by dividing every piece, maybe I should show that work. I'm sure you're all familiar that when you're adding fractions together, as long as the denominators are the same, then you can put them together going this way. Well, now in calculus, we need to be ready to go that way. So I hope now you're convinced that that is correct. So now the derivative, 3 times 3 is 9, x squared minus 3. Done with that problem. Other tricks to the trade is making sure you're familiar with negative, being in the denominator is the same as being a negative exponent. So now the derivative is negative 4 x to the negative third power minus 12 x to the second power. Got to subtract 1. And why is that useful is now it makes sense. Instead of doing the limit process, just as a reminder, because in Unit 1 we did all this limit as h approaches 0, yada, 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 all over h. Now, you just learned a shortcut that you don't have to do all that mess now. And why is understanding exponents so helpful is now you can go back and rewrite it as negative 4 over x cubed, minus 12x squared, which would have been what you would have gotten if you did that shortcut over and over again. Again, you can only do the shortcut if it's written as a series of polynomials. So like we can't do this one yet. We have to multiply it out. So rewrite it. X squared plus 2x plus 3x would be 5x plus 6. And then multiply it out again. Hopefully I'm not making any arithmetic mistakes. You already know that's probably my biggest. Yep, I already made one. 2x cubed. And then we'd have x squared plus 10x squared. I believe that's 11x squared. And then 5x plus 12x, I believe, would be 17x plus 6. I'm going to pause and double check I'm doing this correctly. I believe I'm ready to move on. So now do our 2 times 3, subtract 1. 11 times 2, subtract 1, and then you're just left with 17 for that answer. Again, rewrite. Rewriting will make it your friend. You can divide each piece, so that would be x to the negative second power minus 5x to the negative third power. So now we can find the derivative. And you can rewrite this, but I'm short on time. I just want you to recognize that this is correct. So you can rewrite this as negative 2 over x cubed plus 15 over x to the fourth, and you could combine fractions somehow. I'm not going to do that. Again, this would be something that maybe you look at the exponents. It's a lot of exponent manipulation, so rewrite the function first as 3x when you subtract the exponents. That was a rule for probably you learned in Algebra 1, Algebra 2 maybe, where you bring the 1/3 in front, subtract 1 from that exponent, and then you could rewrite this as 1 over the cube root of x squared, because the negative exponent sticks into the denominator. and maybe I'll do this last one on this page and really emphasize, you know, all the manipulation you can do. So if you were to take the derivative of this, because it is a polynomial, well, you know, the 4's would cancel as we multiply, so we're left with negative 3x 3/4 minus 1 is negative 1/4. And then 1/4 times 2 would give me 1/2 x to the negative 3/4. And so what that means is we have negative 3 over the 4th root of x plus 1 over 2 4th root of x cubed. And honestly, there wouldn't be much point in simplifying any further. So I would just stop right here. You could write as another fraction. The main issue is, you know, is there a multiple choice question that maybe the answer you get doesn't match that one of the 4 options, or 5 options if it's one of my tests. So what you might need to do is do some more arithmetic and simplification to see which one matches that answer. And I sort of want to start this one on its own slide, but maybe what I'll do is introduce to you the premise of the derivative of sine and the derivative of cosine. The derivative of sine of x is, well, you should have learned in pre-calculus that sine is this curve. Right? It goes from 0 to 2 pi. That's 1 full revolution in the unit circle. All right, here's pi. Now, if you remember, the derivative is the slope at a point. Well, if I were to ask you for the slope at each one of these points, now remember, it does go infinite, like it goes on this way and continues on this way. So since I already used that color, maybe I'll just switch to this. So what's the slope at this point? Well, it should be exactly up here at 1. Well, if I get to the slope at this point, it should be exactly 0 down here. If I go to the next key point, this slope is negative 1, which is down here. And same thing, slope right here is 0. The slope right here is 1. So as I graph that curve connecting those dots, what you'll notice is the derivative of sine is the cosine curve, which is awesome. Okay, and in case you didn't realize, cosine does continue on. So this is going to be an important tool to put in our tool belt. Most people just memorize that, by the way. Now I'm going to take it a step further and ask you, what's the derivative of cosine? And this is where students get stumped, because what you first notice is, okay, well, the derivative of the first point is 0, so we're here again. But the derivative right here should be negative 1. And then back down here, the derivative is 0. Right here, the derivative is 1. And then right here, the derivative is back to 0. So what you'll notice, I know my picture is getting messy, but the curve that I get is the same as the purple curve I started with, except it's reflected over the x-axis. So when something's reflected over the x-axis, it's negative. And that purple curve was the graph of sine. So in other words, the derivative of sine is cosine, but the derivative of cosine is negative sine. So most people commit these two ideas to memory, and what I'm going to do is start the next slide actually proving it using what most math teachers would prove. But here's a nice little visual to explain it. Otherwise, commit these two rules to memory.